Another lecture in the series of transducers, ultrasound transducers, also known as probes, scan heads, or scanners. This series discussing the basic components of the transducers, the non-imaging transducers, and imaging transducers. And here in this part, we're discussing the imaging transducers, and we have the mechanical and annular array, one group, array 1D transducers like the phase array, linear array, curvilinear, and tightly curved array. And the array 1.5 or 1.5D transducers, also array 2D transducers, and lastly we'll discuss the 3D and 4D imaging transducers or techniques. So now we come to the array 1D transducers. Before we start, let's have some few words about this expression 1D. 1D is something that sometimes is confusing. This one. Okay. To many of the students, what is this 1D? 1D means that there is one direction of cutting of the PCTs. PCTs actually were manufactured as one slab, and this slab is cut through like fine techniques of laser cutting that in the form of PCT elements. So we have multiple elements of PCTs through cutting, and the cutting here is in one direction. So if this is the slab, like here, and I get cutting by, let me have one color here, so cutting like this. So now I go in one end to one end. So this is here one cutting plane. So this is here 1D. 1D means one direction of cutting. Okay. Later on, we'll know that there is something called 1.5D. 1.5D is what? The same plane cutting here, but then there is different rows. So we have here columns. So we have here multiple columns, but one row. If we have 1.5D, what happened? I have multiple columns and multiple rows, but the rows are of different number. They are less in number compared to the columns. That's why we call it 1.5D. I will discuss this later on in details when it comes to the 1.5D and also in the 2D transducers. All right. So when we mention 1D or 2D transducers or 1.5D transducer, we are talking about the PZT cutting, not the image shape. The image shape, all of these are bringing me a 2D image. So all of these are 2D image, okay, but it's 1D cutting, okay, it means one row. So let's finish this now and let's go to the first example or the first pattern of the array 1D transducers is the phased array. So this is here the phase array, and many people call it the small probe. This is the echo probe. This is the one that is used for scanning echocardiography. One probe, small probe, okay? And this is called the phase array transducer. This phase array transducer, it has a small footprint. This is called the footprint. So this footprint is small size or small area, and that's why it can be used between the ribs. That's why it's very famous to be used in the echo. Actually, is almost the only transducer that can be used in the echo, except for the continuous wave. But this is the only imaging transducer that can be used for echo scanning, the phase array transducer. So let's go in details about this phase array transducer, and we come to the active elements or the PCTs or the crystals or the ceramics. Okay. How about these PCTs or crystals or ceramics? Okay. They are arranged in an array. Array means like assembly or multiple but multiple PCTs arranged together, and that's what we call like a bundle or an array or an assembly. Okay. How many? Most of the transducers ranging from 64 to 128 PCTs or elements. They are arranged as we see here in one direction. So from this side to this side, from one end to an end. So they are columns, but not in rows. These active elements are rectangular in shape. Okay, they are arranged in one straight line. That's why this is why sometimes they call it the linear because they are arranged in one line, straight line. Each one of these active elements is like acting like with the others to form one group. So they are having a teamwork. All the active elements are having a teamwork to form each sound pulse. So each sound pulse of this transducer is formed with the collaboration of all the active elements. So assuming that we have here one sound beam, let's take it like this one. Okay, so I'm having here, assuming that I'm having a sound beam here, right? This sound beam is formed by what? All of them. So all the active elements will form this sound beam. Okay, and now how about the next sound beam? Assuming that I'm having here another sound beam, right? It's formed by what? All of the active elements again will share in the formation of the next sound beam. How about this sound beam? Assuming that I'm having here another sound beam, right? All the active elements will share in the formation of each sound beam. So each one of these sound beams here is formed by what? All of them. So this is something that we need to know, that all the crystals or the ceramics in this phase array transducer, all of them are sharing together, collaborating together to form each pulse. Each pulse, each sound beam is formed by all the transducers, all the elements of the transducer, right? So this is something that we need to know. They are, I like to call them like a teamwork. All of them are sharing in each pulse, all right? So this is here the arrangement of the active elements. How about steering? Steering happens with what? As we mentioned earlier, all of them will share in the each pulse. So if I'm having a pulse that is directed, let's assume that a pulse is directed in this direction, like here, okay? How this happen? Because I'm having what we call phasing. So steering here is electronic by phasing. What is phasing? Okay, I have in the ultrasound machine, there's a part called the beamformer. Beamformer is receiving the electric pulse from the pulsar, take this pulse and then multiplicate this pulse into the many pulses, and each one of these pulses is delivered through one wire. So assuming that I'm having, for example, if I'm having like 62, okay, or whatever the number of active elements, I'm having 62 wires. So each element of these, this is here, like I put them here, you might be able to see this. So here is one active element. Okay, so let me take another color, like here, for example. There's here one active element, there's another active element. Each one of these is having one wire. Each wire is delivering one pulse. So how many pulses are there? Many pulses. Based on the number of PCTs, I'm having many pulses. So these pulses are delivered, but not all of them are the same time. That's why they are called different minute times, minute time delays. So first one to arrive is this one. So assuming that I'm having here, this is here the first to arrive, okay? This one here is the first to arrive, and the last to arrive is this one. So starts from here, ends here. And the active elements are sent in a slope pattern. So this is the slope pattern. So again, if I make them in a simple word, I can call it this way. The steering is by electronic phasing, electronic steering by phasing, meaning that all the electric pulses, sometimes or electric spikes, are delivered with minute or phase time delays and in the form of a slope. So having a slope here, now this will get the beam in this way. So what happened if I want to get the beam a little bit closer to the midline here? What happened? I will send the sound pulses, the electric pulses in a different slope. So I will get, for example, I will get the slope having this direction, like this, right? And then another slope, and then another slope, till I reach to this pattern here. So this and this slope will send the beam in a different direction. So beams with different directions, sound pulses with different directions, are steered via electronic phasing. Phasing means what? Different timing. Phasing means different timing. So different timing of these electric spikes or these electric pulses will, at the end, will deliver me the sound pulse with different directions. Okay, how this happen? Again, by what? By the beamformer. So this fashion or this pattern of phasing is achieved by the beamformer. How about focusing? Again, focusing is electronic. By what? By phasing. Phasing means taking the sound pulses, put them in spikes. Sorry, taking the electric pulses or the electric spikes, deliver them through the active elements, through the wires, and these wires will take these pulses in different pattern. What happens here? The first pulses will be delivered to the far ends of the array. Okay, how about the center will be the last to deliver? What happened? I'll get the sound pulse that is delivered will have a focal point in the center here. So again, these electric pulses or spikes are delivered with minute or phase time delays in the form of curves. So steering in the form of slopes, focusing is in the form of curves. Okay, this electronic focusing is characterized by two things. Number one, they are multiple. I can achieve multiple focal points. I can deliver each pulse with different curvature. So for example, this curvature will give me the focal point, assuming that I'm just uh, drawing some point here. So this arrangement of the active elements will give me the sound, the pulse here, I mean the focus here. Okay. How about if I take another arrangement, take it, for example, this one. So I'm having here different pattern of electric pulses, and I will get it like this. So a shallow curve. What happened? I will get the focus here. So different curvature will give me different focal points. So I have multiple focal points based on changing the curvature of the electric pulse or voltages delivered to the active element. So again, I have multiple focal points through what? Changing the curvature. Second characteristic of this electronic uh, focusing is I can get adjustable focal points, adjustable location. I can make them shallower or deeper again through what? Through changing the curvatures here. So I may have multiple focal points and also they are adjustable in location. I can make them shallower or deeper. Okay, how about the elevation resolution? We know that there is something called lateral resolution, and this is achieved by focusing, the one that we just mentioned now, and this is transmit focusing for the lateral resolution. Now, how about the elevation resolution? Elevation resolution here is focused through mechanical focusing. Okay, and actually, mechanical focusing in these 1D array transducers, all of them, like the phase array, the linear and the curvilinear, and the endovash or the endorectal, all of these are having one pattern of elevational resolution, which is mechanical focusing. Mechanical focusing is what? Okay, they put either acoustic lens along the whole face of the transducer like this, or they put or cutting the PZTs in curved pattern like here. These two methods, they will bring me the slight thickness focus at a certain point. So there is here mechanical focusing for the elevation resolution. So the thickness of the sound beam, if I have here the sound beam, like here, okay. So I can get here, the thickness is focus, but this focusing here is one focal point only. So I get here again, the slight thickness of the sound beam is focused along the thickness of the elevational, okay, by mechanical focusing, by putting a acoustic lens like this one, or cutting the PZTs in a curved pattern. This one or this one will bring me slight elevation resolution focusing by mechanical. Somebody will say mechanical, we just knew that mechanical focusing was used in the mechanical probes long time ago, right? Yeah, but now this is the only application. Okay, we need to know this fact. The only application of mechanical focusing nowadays is in the 1D transducers. 1D transducer like the phase array, curvilinear and linear probes, and the endovaginal probe or endorectal probes. All of these are 1D transducers that are having elevation resolution focus mechanically, right? The image is sector. Why? Because I like to mention earlier that the face or the footprint of the probe is small, very small. So, and through this steering pattern of the electronic phasing of the sound pulses, okay, what happened? I will get all of the sound pulses as if they are coming from the same point from the transducer. All the pulses are coming from the same number of elements, which are the whole elements of the transducer. That's why, as if they are coming out from the same point. And when they are steered from side to side, it will bring me a sector image, sometimes called the fan shape or triangular or wedge shape. All right. So this is the image shape. We need to know something here. It's important to mention that the only transducer that nowadays that bring me a sector image is this one, the phase array. Okay, why I need to know that? Because sometimes if you have an image that is a sector shape and somebody will tell you, okay, this image is formed by the mechanical or the annular phase array. You say, yes, this is true if we have this like many decades back. But nowadays we don't have mechanical, we don't have annular phase array, and that's why the only transducer that can bring me a sector image is the linear phase array transducer. All right. So currently, the only sector image is the phase array. Right. In the past, we used to have two transducers, but nowadays, the mechanical and the annular phase array, but nowadays they are no longer in the market because they are obsolete almost. Okay, and the manufacturers never even manufacture the like spare parts for these imaging transducers. So that's why the only transducer, again I'm repeating, the only transducer that can bring me a sector image nowadays is the phase array. Okay, what happens if I'm having damage element? As we mentioned earlier, we have like many images, like one, for example, 128, right? So if I'm having uh, more than more than 100 elements, okay, if one or two of them is damaged, this will not affect the image uh, uh, tremendous effect. I will get light effect in the image quality or in the image steering, but it's not. I will get blurred image, but not complete damage. So I get even if I'm having damaged elements, some of the elements are damaged, I will get only blurred image or abnormal steering or focusing. Applications, like I told you here, this is the sector image, and this is the small footprint, and this is the transducer, okay? How we can use this? This small footprint, we can apply it between directions. That's why this is the only 1D transducer, that is imaging transducer, that can be used for scanning the heart, imaging transducer, okay? Sometimes we are using the continuous wave for echo, but this is not an imaging transducer. I'm talking about imaging transducers. We are talking about the only imaging transducer is the phase array. So the main application is what? Echocardiography. Why? Because I'm having small footprint and it can be manipulated between the ribs. So this is an advantage, right? So since we are scanning the heart, are we using what type of active elements? The high frequency or low frequency? Of course, lower frequency, we need deeper penetration. And that's why, because we are having here a transducer that has an advantage of having a small footprint. And in the meantime, it's using lower frequency elements, and this pattern, we can use it also for abdominal scanning, because sometimes in scanning in the abdomen, you might have some difficulty with the ribs, scanning, for example, the spleen or kidneys, or sometimes the liver. You might have some difficulties with the ribs. So if you use such a transducer in between the ribs, that will help you tremendously to get a good image, because we're having a deeper penetration, and in the meantime, is having a small footprint that will not have the problem of rib shadows. So again, using in the abdomen, intercostal imaging, OBGYN, and also sometimes it could be used in the transcranial Doppler, but this is a limited application because it needs specific software application and a calculation package in the machine, and you can use the same probe with the very lower frequency, for example, 1 megahertz. So this is a limited application, but sometimes it could be used in the transcranial Doppler too. Thank you, and I hope that was helpful, and see you later in another lecture.